Okay, so when you guys are studying for your test, and I sort of tell you that there's 7.1 and 7.2 is on the test, that's essentially nuclear fission and nuclear fusion, and of course some calculation questions relating to those. Now, as I've said, nuclear fission is the one that really, I guess, we can harness on Earth. This sun, the process of the sun converting or fusing hydrogen into helium is nuclear fusion, but here on Earth we can't do that. We essentially can't. There's no practical ways of doing that. It would be great if we could provide a lot of energy. Obviously, the sun has tons of energy, which we see in the forms of heat and light and so on. So for fission, we can think of, say, things such as nuclear power plants, which is a controlled process of essentially splitting the atom. Now, what atoms are we looking at? We're looking at atoms which have a really big atomic mass, such as uranium-235 or plutonium-239. What happens is that neutrons or particles are fired at these massive atoms, and what happens is they're essentially splitting. That splitting forms what was that? What would we, this picture here, what would that be? What would that be? What do these look like? Little, starts with C? Chains, yeah? It forms a chain reaction. And that chain reaction essentially can be controlled in, say, a nuclear power plant, or can just be out of control in the case of a nuclear bomb. Okay? Huh? So, as I have said to you, nuclear fusion, the sun. Think about hydrogen forming into helium, fusing. In actual fact, though, what we have is say, something like hydrogen 1 meets up with hydrogen 2, and then that essentially forms helium. Okay, so you've actually got in the process of nuclear fusion in the sun, you've got hydrogen 1. In other words, it does not have a neutron, and meeting up with hydrogen 2, and effectively those coming together to form helium. That's essentially the process of what the sun's doing. That is a release of energy, and that release of energy is what we sort of obviously experience from the sun. Just one second. Obviously, if we are thinking of the energy that can be created from either fusion or fission, we're thinking about vast amounts of energy. We've controlled, that is essentially where the nuclear bomb, or the process of how a nuclear bomb works. Now, just quickly, if we want to start doing some physics and some maths revolving around this, let's look at some numbers. Now, first of all, I'm going to say to you that the formula related to this is E equals mc squared. Now, be careful, this m isn't just it's the deficit of mass. Okay, it's the deficit of mass. So in other words, the loss of mass when that atom is splitting. Now, so that is m. Now c is the speed of light, which is extremely fast. I think it's 300,000 meters per second. Speed of light, which is equal to 3 by 10 to the power of 8 meters per second. Now you can see the power of even just a small mass which is travelling at close to the speed of light. Okay, so because the speed of light, the speed of light is squared. So that's a huge amount of energy. Now I'm just going to pause the video here, and I'd like you to sort of have a look at this one and have a go at this question just in your exercise books. Try to have a go at it before I go through it with you. When we get to this, just quickly though, this equation here, the energy is in joules, but it might be worth noting that we can also work it out in electron volts, because joules, it might be a small amount, a small amount of energy, but that's a massive amount of energy for such a small particle. So we're going to be showing you how to work it out in electron volts in a moment. But what I'd like you to do is just see if you can have a go at this example based on what we know, and also I might just zoom in a little bit more. So have a go at this one. All right. So for this question, the first one's asking how many neutrons are released during the fission process. In other words, what is the value of X? Well, if we have a look at the left-hand side, in other words, we look over here, we have 240 nucleons and we have 94 protons. So that means that we need the same over this side. Now 145 plus 93 is equal to 238. 238 nucleons. We know that 56 plus 38 equals 94. 56 plus 38 equals 94. So therefore, we have a neutron. There's obviously just one neutron. So we therefore have 2 neutrons that are released during this fission process. So there are 2 neutrons. Yeah, I'm just putting it on the video. Now, during this one, we can say that the energy of the mass deficit released during the fission process is E equals mc squared. And we're told what the mass is, 3.07 by 10 to the power of minus 28, always in kilograms. And the speed of light, which is 3 by 10 to the power of 8, and it's squared. Now, that's going to give us an answer in joules, which is going to be a very small value in joules, but for such a small particle, that's really quite a high value, a big amount of energy in terms of an electron volt, which we'll get to in a moment. Now, if I go ahead and do that, I get my calculator out, and of course you guys wouldn't have a CAS calculator in your exam. No, you do. You cannot use a CAS calculator in your 11 or 12 physics exams. Wouldn't it be nice? Couldn't you just put all these wonderful concepts and things in there? So we are going to... Oh, I don't want scratch pad. It does funny things. Okay, so we've got... what was it? 3.07 by 10 to the power of minus 28. 10 to the power of minus 28, and that is multiplied by 3 by 10 to the 8 meters per second, and that is squared. So our answer in joules is going to be 2.76 by 10 to the power of minus 11. 2.76 by 10 to the power of minus 11 joules. Now, what we're going to say then is the elementary charge we discussed and we went through this in the electricity section was 1.6. The elementary charge was 1.6 by 10 to the power of 19 coulombs, wasn't it? Charge of an electron. Okay. Now, as it turns out, if I was to divide this by 1.6 by 10 to the power of minus 19, that's actually going to give us the electron volts. The electron volts, because a lot of the time that's what we're asked to find. So, dividing that result by 1.6 by 10 to the power of minus 19, that is going to give us an answer in electron volts. So we've got 1.73 by 10 to the power of 8. 1.73 by 10 to the power of 8 electron volts. Okay? Or we could say that that is 1, 2, or that's about 173 mega electron volts, which is really quite a massive amount of energy for something which is so small. Absolutely. Yes. All right, so you've been given the chemical equation there. You can see here that we've got a neutron fired at a very high speed at uranium. That breaks off, nuclear fission in other words, and there's a massive amount of energy released. And what we need to do is we need to calculate what that energy is. The energy is equal to mc squared. And the mass of the defect during this reaction is 2.12 by 10 to the power of minus 28. And then I'm multiplying that by 3 by 10 to the power of 8 all squared. That is going to give me a value in joules, of which we will work that out to be 2.12. So 2.12 by 10 to the power of minus 28 by 3 by 10 to the power of 8 squared, and you should get 1.9 by 10 to the power of minus 11 joules. 1.9 by 10 to the power of minus 11 joules. Now that's a very small number, but so of course a lot of the time we relate it to an electron volt. So to find the energy in electron volts, we must work out the energy in joules and divide it through by the elementary charge, if you like, 1.6 by 10 to the power of minus 19. So I will divide that by 1.6 by 10 to the power of minus 19. You're going to use this value a hell of a lot in physics, so you will memorize that, I can assure you. No, that's actually incorrect. I've done that incorrectly. So let's do this again. And I'm going to divide, and I'm going to use brackets this time. 1.6 by 10 to the power of minus 19. That's a lesson that you really should learn. Use of brackets very important especially when you're using a scientific calculator. 1.19 by 10 to the power of 8 electron volts, or if you like, I could say that's approximately 119 mega electron volts. 119 million electron volts. All right, now essentially, if from what I've just done in this video, which now is I'm going to stop, and that goes